Hello everybody and welcome to our presentation about our paper called ExMaps long-term localization in dynamic scenes using exponential decay. So we start by defining what the problem we are trying to solve is. What is long-term visual localization? It is pretty much estimating the camera pose from a query image against a point cloud in our case, given that the environment has changed over time. And this is visible in the bottom right image, where we can see two query images with differences over time. Localization can be divided into three main categories. The first category is image-based, where an image is matched against a database of images and poses, and then a pose is returned. The second category is structure from motion based, where key points in the image are matched against 3D points descriptors in a point cloud, and using a solver, a pose is returned. And the last and most recent approach is by using machine learning based methods where, for example, a pre-trained neural network tries to predict a pose for an image. Here we see a typical structure from motion based localization pipeline. In our paper, we utilize multiple user sessions. And by user sessions, we mean a set of frames successfully localized in a point cloud. As we do this, we keep the descriptors over time for each 3D point. Thus, we end up with a point cloud that we call a live map. A base map is a point cloud that was constructed at one point in time, and we use a live map and a base map for comparisons later on. Here we see a visibility matrix that can be extracted by structure from motion software. And here we see how we apply the exponential decay per image and per 3 sessions. Now we end up with two scores. We end up with the stability score per image and the stability score per session for each point. If we sum the columns, then we get two different distributions. The stability per image score can differentiate between images where the stability per session score cannot do that. The higher the score, the more stable the point is. We benchmark our method on two different datasets. The first one is the CMU extended seasons dataset, and the second one is the retail shop dataset that we introduce in this paper. For each dataset, we construct a base map and a live map. We immediately see an increase in the number of matches between the live map and the base map, with the live map returning a higher number of matches. We also see a difference between different versions of Ransack and Prozac between a base map and a live map. And to be more specific, we see a difference between using Prozac with the default score in the base map with using Prozac with our score in a live map. We see an increase in inliers, and we see a reduction in translation and rotation errors as well. In addition, we show that as we add more data over time in a live map, we notice an increase in performance, meaning that it takes less time for Prozac and Ransack to return a pose. And also we notice a reduction in translation and rotation error as well. And to summarize, in this paper, we introduce the effect of time using exponential decay. We notice that by doing so, we can improve Ransack and Prozac performance. We can increase the number of matches by introducing a concept of a live map. And we also show that live maps can improve performance over time as more data is added to them. And I would like to thank everybody for their time today. Bye.